Okay, so here's some more notes on 4.3 and some definitions and things we'll talk about. Concavity, the graph of a differentiable function, y equals f of x is concave up on an open interval if y is increasing on I, that is, the derivative is positive. And if you go back and look at the little example I gave you over here, you can see that if you remember, the slope is increasing. It's negative, but less and less negative. It gets to be zero, then positive. So here it's concave up because the y prime is increasing. The slope is increasing. That means its derivative is positive. Its slope is positive. So I kind of wrote that here to combine this. And then a graph of a differentiable function, y equals f of x, is concave down on an open interval I if y prime is decreasing on I. That means the second derivative is negative. And here's a situation. Here it's positive, but it gets less and less positive to zero, and then it starts to get negative. So here the slope is decreasing. That means its derivative is negative, and it's concave down. So that's what they're talking about. And these are definitions in the book. And then we have the concavity test, which is basically what I wrote down here already. The graph of a twice differentiable function, y equals f of x, is concave up on any interval where the second derivative is positive, and concave down on any interval where the second derivative is negative. Now, a point of inflection. Okay, and this is important. The point where the graph of a function has a tangent line, that means it's differentiable, and where concavity changes is what we call a point of inflection. Okay, so where concavity changes is called a point of inflection. Okay, so we have to find those things. So let's try this, and this is what we usually call the second derivative test. There's another application for this, but for the second derivative test, but our basic one is for finding concavity and points of inflection. So let's take a look at an example. And this is kind of a velocity function, but we'll just call it f of x for now. Or y equals 2x cubed minus 4x squared plus 22x minus 5. And we want to check for concavity. And points of inflection. Okay, so right away when I'm talking about that, I'm talking about the second derivative, not the first derivative. So let's take the second derivative of this. So we have to take the first derivative first. So y prime equals, it's going to be 6x squared minus 8x plus 22. So that was easy. Then we'll take the second derivative. Y double prime equals 12x minus 8. Okay. Okay, so I guess this is all right. Okay, so let's take a look at this function. I kind of forgot something when I copied it down, but that's okay. This will work. Okay, so this is my second derivative. So we just do a second derivative test. This is pretty easy. And we'll call this y double prime. Okay, and we want to see again where this is equal to, where this is going to be positive, negative. So we set it equal to 0 to find out, what's happening with our signs. So let's set y double prime equal to 0. It's not going to be undefined because it's a straight line, so we can just set it equal to 0. Y double prime equals to 0. So we have, that implies 12x minus 8 equals 0, or 12x equals 8, or x equals 2/3 divided by 12. So that's going to be a critical point, or a possible point of inflection. Now we just have to check and see what's happening for concavity. Remember, we know if the second derivative, if the second derivative is, go back over here, if the second derivative is positive, it's concave up. If it's negative, it's concave down. And where concavity changes is a point of inflection. All right? So let's see if it does change. So if I put 2/3 in here, I have to put a number that's smaller, so let's try 0. That's nice. And that's going to be negative, obviously. So that's looking good. And let's try 1. If I put 1 in here, 12 times 1 is 12 minus 8. That's positive, so definitely we've got something going here. Now, what we usually do on here is just write down, this is going to be concave down. So my graph should look something like this. It's going to be concave down, because it's negative. It's easy, down, negative. And you can say that you're frowning. Sometimes they say when it's concave down, it's negative. You have a negative attitude, so you're frowning. And when it's concave up, that means you're up, you're happy. And it's positive, so sometimes you can see it's something like this. So I usually draw something like this to let us see what's happening kind of with the graph, because that's the concavity of the graph. And it looks like we do have a point of inflection because concavity changes. Now we'd have to put this value into the original function, which I don't really want to do right now. So sometimes we can just say at the x value rather than find out what the y value is, because sometimes these are tricky. So we can say at x equals 2/3, comma, there is a point of inflection because concavity changes. There. So when x is 2/3, now we can find the y value later. So that's a point of inflection. And we also want to check for concavity. So where is it concave up? Well, it looks like it's going to be concave down anyway. Concave down. And the interval will be negative infinity to 2/3. We usually use that open because concavity is changing right at 2/3. It's concave up. From 2/3 to positive infinity. And we have a point of inflection because concavity changes, all right? And you could probably put that in your calculator and graph it just to see what it would look like. And when you did that, you could actually find